Today's lesson comes from section 2.5, inverses of functions. You can see the learning goals for today. Find the inverse of a relation or function and determine whether the inverse of a function is a function. So our definition that we had established for a function is going to come into play quite a bit today. All right, let's start with if we know what a function is, then its inverse. An inverse of a relation is when the domain becomes the range and the range becomes the domain. The ordered pair xy becomes yx. Some people's simpler version of that would be switch x and y, flip-flop x and y. Those are typical. Let's go back to that last slide and finish up with to find an inverse, you have a couple things you can do. You can take an ordered pair or a set of tables and find an inverse. You can take an equation and find its inverse, and you can take a graph and find its inverse. So there's one thing called an inverse, but several different ways to find an inverse. And it does apply to the rule above. So we'll be going through all those different things as part of our lecture today. Let's start with our vertical and horizontal line test. We knew that we could run a vertical line through any graph, and we would be testing to see whether that graph is a function. The vertical line would allow each and every x to be paired with one and only one y, our definitional function. A quick way, without having ordered pairs in front of us, to tell and get a snapshot of whether our graph is a function. So on the two that I've done, the wave, I've ran vertical lines through it, and it appears to be a function, only each vertical line is getting hit once and once only by that graph. The parabola, same thing, once and once only. Does it hit the graph or the vertical line? So we're good. The circle, for example, is definitely a no. It is not a function. So we're looking at the original ones, and let's go with a red here. So we said, yes, this would be a function. Yes, the parabola would be a function, but no, the circle would not be a function. And you can look at the other ones and take a guess, figure out what they would be, functions or not, and be ready to discuss it for class. Now, vertical line test tested the original graph to see if it was a function. A horizontal line test would allow us to draw horizontal lines through that same original graph. In doing so, when we draw horizontal lines through any of our graphs, and it can be numerous horizontal lines, it does not have to be just one. So infinite horizontal lines drawn through our graph should show whether the original graph's inverse is a function. Because think about it. If we're testing a vertical line, we're basically testing how many x values share a y. But if we test a horizontal line now, the x and y's have been flipped in an inverse, and so we're testing the y values. So if we come back and quick recap, the blue horizontal line tells us that the inverse of the red graph would not be a function. Here as well, the inverse would not be a function, and in the circle, it would not be a function. Some people say, is it always not? And that'll be a discussion we can have in class, but look at the other ones. Run your vertical line test on it, see if they're functions themselves, then run the horizontal line test on it to see if its inverse would be a function. Now, as a recap also, definition says vertical line test tests whether the graph itself that you're looking at is a function. Where the horizontal line test tests whether the inverse of that graph is a function. And when we say the inverse of the graph, it's like we don't see that. We would have to draw the inverse. This saves you time and not needing to draw the graph. There are a couple other combinations before we go on to some practice problems. Vocabulary. If you have a function that is said to be one-to-one, you can see the inverse is also a function. So if you have something that is a function, an equation, a graph, a set of word pairs, then its inverse must also be a function in order for it to be a one-to-one function. Identity function, if you have the function f of x and it equals x, then we are saying it is the identity function. And the identity function is this I of x. So it comes out to what you started with. That's the identity. From there, we also have a way to test whether two functions are inverses of each other. And that is if f and g are our functions, and f of g of x and g of f of x. So notice we're doing both. Reminder also that means f follows g of x, and then in the second one, g follows f of x. And they come out to be, again, the identity function, which was the x, or what you started with. So we're going to try and test both of those ideas on a couple problems. So if we start off with just ordered pairs, simple ordered pairs, it says find the inverse, and then state whether the inverse is a function, and state whether the relation is a function. So let's start with the first ordered pair, first set of ordered pairs. 1, 2, 4, negative 2, 3, 2. If we followed our definition, flip-flop x and y, then we'd simply have 2, 1, negative 2, 4, and 2, 3 as our new set of ordered pairs. That ordered pair has to be tested to see whether it is a function. So we'll start, this is our new or our inverse, and we'll call this the original. So the original set and the inverse set. Now, when we look at that inverse set, and we're trying to determine if it's a function, 2 is paired with 1, negative 2 is paired with 4, 2 is paired with 3. It's that 2 is paired with 1 and 2 is paired with 3 combination that should raise a question. That being, every x value is paired with exactly one value of y. In that case, 2 is paired with 1, 2 is paired with 3. It is not a function. So we would say no, it is not a function. And then lastly, state whether the relation is a function, which means state whether the original was a function. 1 is paired with 2, 4 is paired with negative 2, and 3 is paired with 2. Each x is paired with exactly one y. We're good to go. Yes, this is a function. Now going with that idea, you can try that second one, and it'll be up for discussion during class, or any other ordered pairs you can think of that you want to test. Bring those ideas with you to class. All right, here's 2 problems, but let's do them one at a time. So let's start with, if I wanted to find an equation for the inverse, and I had y equals to start with, if we go with our definition, flip-flop x and y, then right away brain has to be saying, I'm going to be thinking x equals 2y plus 3 divided by 5. And if we said face value, is that an inverse? Well, yeah, but mathematically we've always solved for y. If we were going to graph something, if we were going to compare 2 equations. So again, that's probably the focus. So yes, we flip-flop x and y. We have our inverse equation, but it's not really in a form that we're used to working with, comparing. So let's do that next. And the first step would be to get rid of the divide by 5. So we times both sides by 5, and we would get 5x equals 2y plus 3. We'd subtract 3 from both sides and get 5x minus 3 equals 2. We would then have to divide both sides by 2. That would leave us with our final equation of y equals 5x minus 3 all divided by 2. If you wanted to rewrite that, yes, you could have y equals 5 halves x minus 3 halves, and that would be appropriate as well. In other words, divide the 2 into both parts. So there's our equation in proper form for the inverse. It is solved for y. You need to keep that in mind. Anytime you're writing an equation, you want to have y by itself. So look at the original equation, y by itself, and compare that to the inverse, y by itself. You have some characteristics that are similar, you have some that are related, but they are definitely inverses. The one equation should undo the other. Okay, from there, let's go back and show whether f of x, which is the statement 4x minus 3, and g of x, which is the statement 1/4 x plus 3/4, are inverses of each other. And if you recall, our definition was f of g of x and the other direction, g of f of x, both must be performed on our functions, and we have to get back to x, which is also known as the identity function. Okay, so you have to get back to what you started with. What you were putting in has to be what you get out. All right, so let's go first and do f of g of x. With the two functions listed here, that means we start with g of x. So we're going to start with 1/4 x plus 3/4. That is our g of x. There's nothing to do there because you can't add the fraction with the variable. So we now have to put that into the f rule wherever there's a variable. The f rule says 4 times your variable. So that's going to become our variable. So 4 times our variable minus 3. Let's simplify so we can see what happens. And we would get 4 times 1/4 is 1x. 4 times 3/4 is 3. And then subtract 3 on the outside, and you can see 3 plus 3, or 3 minus 3 is what remains. And we do get 1x, or just x if you like. So the first part, f of g of x, looks good. We came back and got what we started with, which was x. Now let's do the g of f of x, which means we start with f of x. So this time we're going to start with 4x minus 3. There's nothing we can do to that. No adding or subtracting can do because of the variable. And so that becomes our number. That number will now have to be put into the g rule wherever there's a variable. So here we go. 1/4 times our variable. So 1/4 times our variable, 4x minus 3, plus the 3/4. And again, using order of operations, we will multiply. 1/4 times 4, 1x. 1/4 times a negative 3 is a negative 3/4. Negative 3/4 will get added to 3/4. And we do combine like terms. And again, we end up with 1x, also known as x. And we have just shown that putting f of g of x and g of f of x in both directions and doing their simplifying, we get x out. So we have shown that these two equations are truly inverses of each other. Now, quick comment. If the first one would have come out to x, we still have to do the second one. If the first one comes out to x and the second one comes out to, let's say, 3x plus 2, then we know they are not inverses of each other. Or vice versa, what if the first one would have come out to 3x plus 2? We truly could have stopped right there, not tested the second one, because they're supposed to, according to our definition, both come out to be x. And if the first one does not, then they are not inverses of each other. So bring questions about the definitions, how to write inverses, whether it's an ordered pair, equation, or graph with you, and have those other ones worked down, especially questions on vertical and horizontal line tests. Those will be some things we discuss in class. So that's all for today.